So we call the sine, cosine, tan the primary trig ratios. Secant, cosecant, and cotan represent what we call the reciprocal ratios. So our primary trig ratios, sine, cosine, tan, relate to these ratios here. And cosecant is defined as the reciprocal of sine. So we define it as the radius over y. The secant goes with cos, so cosecant goes with sine, secant goes with cos. And we can say that the secant ratio is the reciprocal of cos, so we make that r radius over x. And the cotan is the reciprocal of the tan ratio, so it's just x over y instead of y over x. So these are just the same kind of ideas, but just reciprocal forms. And sometimes the reciprocal forms are going to be more useful to us, so we want to be able to define them. We still use the primary trig ratios, sine, cos, and tan, the most. Okay. Now in this diagram here, again, we're dealing with a unit circle, so because it's a unit circle, we are able to define the ratios as lengths in the unit circle. So this is my unit circle, it's radius 1. And as I've defined before, my cosine is going to be the horizontal length that defines that angle theta. The sine is going to be the vertical length. Let's define the vertical length for sine for that angle theta. And the tangent is this tangent line on the outside. There's a reason why it's called tangent is because it just touches the outside line. And it's the length or height of this line in standard position in a unit circle, okay, because this is going to be, the slope is rise over run. If my run is equal to 1, that green line is my rise. Well, that would be my unit rate for rise, which is in my tan ratio, okay, and so this length is the same as the tan ratio, okay. So when we look at the reciprocal ratios, then the reciprocal ratios actually can also show up in the unit circle. Okay, so these aren't as important. These 3 lines are the most important. So you can do everything with just those 3 lines. What we're going to show you next is just a supplement. It can help us out, and it can also help us understand some of the identities that we end up looking at later on. So cosecant is a reciprocal of the sine. So it's going to be the radius over y. Okay, so it's going to be instead of y over the radius, it's going to be radius over y. Okay, so there's the y. Now we want to make the y value equal to 1. Okay, if I make the y value equal to 1, that length up, this value up top, is going to be the cosecant ratio, and I can then find it in the circle somewhere. So there's my y value, okay, y over the hypotenuse or radius. Okay, or reciprocal, so we're doing radius over y, and we're going to make the vertical equal to 1. Well, the vertical line equal to 1 is right there. Okay, so what would be the equivalent hypotenuse line? Well, it's going to be this line right there. Okay, so that line all the way to G. So A to G is going to be the line I'm looking for. Okay, so it's going to be AG, the line AG. So that angle then is going to give me, that's going to give me the hypotenuse over the opposite side, because remember these 2 angles are the same. So there's my opposite side, hypotenuse divided by 1. Yeah, that's going to be the cosecant ratio, which means in the unit circle, that line is a cosecant length. Okay, so I'm going to just highlight that. So that blue line is my cosecant length. Okay. All right, so what about secant? Where is the secant going to show up? Okay, so secant shows up like this. So the cos ratio is the x divided by the radius. Okay, so we're going to do the radius divided by x. Okay, so radius divided by x is going to be our secant ratio. So I want to find the equivalent radius length if I make my horizontal length 1. So if my horizontal length is 1, there's my horizontal length here. which I'll highlight in yellow. That's my horizontal length. The hypotenuse length is going to be this one here. I'm just going to see if I can highlight it from here to here. Okay, so that becomes my hypotenuse length. So the hypotenuse divided by 1, the adjacent side 1, is going to give me the secant ratio. So I'm going to do that. That's the purple line. So that line is from A to E. From A to E. So that line represents my secant length. And as I talked about before, now you can see that I have this triangle here. It's the right triangle made with the green line, which is tan. So I end up with this relationship. Tan squared plus 1 squared equals a hypotenuse, which is secant squared. So this is what we call a Pythagorean relationship. Okay, and there's this identity that shows up because of that, the fact that we can define that diagonal line as the secant line. Okay, so last thing here is my cotan line. So basically I need to know, this is my rise over run, so I need to know run over rise, okay, or x over y. So my y value I need to make equal to 1. Well, where's the y value equal to 1? Which line is that? That's going to be this one right here. A to f is equal to 1. Then I need my run value. Okay, there's my run value. That's my x value. So this is, look at this triangle here. This is my slope triangle here. Okay, so I'm going to use the same slope triangle, but now I'm going to make my rise equal to 1, because that's in my denominator, and my run equal to my x. And that I'm just going to do in a different color here. I'll do this in green. So that line right there, f to g, is my cotan length. Okay, it's the ratio when the y value is equal to 1. So that's going to be, just going to do that here. So fg represents the cotan length in the unit circle. Okay, and then we then also now have this relationship. We can say that cotan squared plus 1 squared equals the blue, which is cosecant squared. And so that relationship is another Pythagorean relationship that we can come up with. And I'll write it out like this. Okay, I'll just shrink this so you can see it at the same time. So 1 squared plus cotan squared is equal to the blue line, which is cosecant squared. Okay, and that comes from this relationship. So these are just kind of extra ones, and they're nice to know. What's really important though is that we don't really need these ones, these lengths in the unit circle as much, because we could do everything with just the cosine length, A to C, the sine length, B to C, and the tan length, E to D. And those would be values that we can use to define any lengths in the unit circle. The other ones are just nice to know because they do actually show up in the circle, and they do help us understand some of these identities that we will see later on. So these are the identities I was just talking about. Okay, so our tan squared, okay, plus 1 squared is equal to secant squared. So there's one of the identities. So cotan squared plus 1 squared equals the cosecant squared. So that long length is my cosecant. Okay, we have cos squared plus sine squared equals 1. There's another Pythagorean identity. And we can see that these are all things that we can manipulate now, knowing that we have lengths in the unit circle. So this is the main reason why we want to use unit circles, because it allows us to use some geometry now, some length geometry, to be able to work out new things, new relationships.